In today's lesson, we're going to learn about L'Hopital's rule, which is a way of finding limits of functions, of rational functions that are in the indeterminate form. So if you want to find the limit of f of x over g of x as x approaches c, and when you plug it in straight into the limit, do direct substitution, you get the indeterminate form, either 0, 0, or plus or minus infinity over infinity, then you use L'Hopital's rule. L'Hopital's rule says to evaluate this limit, I simply take the limit of, and then I take the derivative of the top function divided by the derivative of the bottom function. And that'll give us our limit value. So let's look at example 1 here. We'll find the limit as x goes to 0 of e to the 2x minus 1 over x. So let's try direct substitution, replacing every x with 0. On the numerator, I get 0, and on the denominator, I get 0. So this is an example of the indeterminate form. So applying L'Hopital's rule, I'm going to take the derivative of the top, which will give us 2e to the 2x, and derivative of x is 1. And then I'm going to do direct substitution, replacing every x with 0, and I end up with 2 as my answer. If you apply L'Hopital's rule and results with the indeterminate form, then you have to apply it again, and sometimes you have to do it repeatedly. So we're going to look at example 2, but I'm going to do another problem. So let's cancel that one out, and let's instead figure out the limit as x goes to 0 of x minus tangent of theta divided by x minus sine of theta. So direct substitution, to evaluate this limit, I'll get 0 minus tangent of 0 over 0 minus sine of 0. So that's 0 minus 0 over 0 minus 0, which is 0 over 0. So let's apply L'Hopital's rule. So I'm going to take the derivative of the numerator, which will give us 1 minus secant squared theta, and then the derivative of the bottom, which is 1 minus cosine theta. Okay, trying direct substitution again. I get 1 minus secant of 0 squared, which is 0, and 1 minus cosine of 0, which is 0. 1 minus 1 is 0. So I still have the indeterminate form. So apply L'Hopital's rule again. So now I'm going to take the derivative of the numerator. In order to take the derivative of the numerator, I need to set u equal to secant theta. And the derivative of secant theta is secant theta tangent theta. So that would give us negative 2 secant theta, take derivative of the outside, times the derivative inside, secant theta tangent theta. And then in the denominator, the derivative of 1 minus cosine theta is just simply sine theta. Okay, let's try simplifying this down a little bit. So I get negative 2. And remember, secant is 1 over cosine, so that'd be 1 over cosine squared. And then tangent is sine over cosine. And if I'm dividing by sine, I could rewrite this as a limit as x goes to 0 of negative 2 times sine of theta over cosine cubed of theta times 1 over sine theta, which gives us negative 2 over cosine cubed theta, which is negative 2, which is just simply negative 2. All right, so in this next example, applying 0 from the positive side, 1 over 0 gives us infinity. And then e to the 1 over 0 gives us infinity. So this is an example of infinity to infinity. So applying L'Hopital's rule, I'm going to take the derivative of the numerator. And that gives us negative 1 over x squared. And the derivative of the denominator using the chain rule is going to give us e to the 1 over x squared times negative 2x cubed. Let's clean that up a little bit. Okay, that'll simplify down to the limit as x goes to 0 from the positive of negative 1 over x squared divided by negative 2e to the 1 over x squared power divided by x cubed. So we're going to flip and multiply the bottom fraction. And this will simplify down to the limit as x goes to 0 from the positive direction. The negatives cancel out. 2 of the x's cancel out to leave us an x on top, and 2e to the 1 over x squared power. Plugging in our 0. Doing direct substitution, we end up with 0 over 2, which is 0. Okay, now we're going to find the indeterminate forms and if it's 0 times infinity or infinity minus infinity. First thing we have to do is some algebra, and we have to convert it back into the 0 over 0, infinity over infinity form, and therefore we can apply L'Hopital's rule. So looking at this, if I just do direct substitution, plugging in infinity, I end up with 0 times infinity. And so I need to do some algebra. And the algebra I can do. Okay, we're going to first move that e to the x down to the denominator, make the exponent positive. And we got the square root of x over e to the x. Doing direct substitution into this, we get 0 over 0. So we're going to do L'Hopital's rule. And that gives us 1 over 2 the square root of x divided by e to the x. Now if I flip that bottom fraction of e to the x over 1, I end up with the limit as x goes to infinity of 1 over 2 e to the x times the square root of x. Now we're going to try direct substitution again. And we get infinity on bottom, 1 over infinity is 0. So our answer is 0. Okay, remember there are some other forms of the indeterminate function, and so what do we do if we end up with some of those forms? More exactly, what if we have an indeterminate limit of the form 0 to the 0 power, 1 to the infinity power, or infinity to the 0 power? So if that happens, that means we have a variable base and a variable exponent, so we're going to use logarithmic differentiation. Remember we did that in Cal 1, you have to hit it with a log, each side of the equation with a log. So example 5 does this, because when I plug in my pi over 2 into this function, I get 1 over infinity. So that's that indeterminate form. So what I'm going to do is I'm going to let L equal my limit equation. And then I'm going to start by taking the natural log of the left-hand side and the natural log of the right-hand side. Now remember, because of the limit notation, I can move that natural log inside my function to have the natural log of sine x to the secant power. And then what I'm going to do is I'm going to use our power rule of logarithms, move the exponent outside the logarithm. And so now I have a product, and when I do this product, direct substitution of that limit, I get infinity times 0. So that means I need to do some algebra. And so I can rewrite secant as 1 over cosine. So this becomes the natural log of sine of x divided by cosine of x. And trying direct substitution again, I get 0 over 0. So now I finally can apply L'Hopital's rule, because I have that indeterminate form of 0 over 0. So if I take the derivative of the natural log of sine of x, it starts by taking the derivative of the outside function is 1 over sine, and then times by the derivative of the inside, which is cosine. So that's cosine over sine, and the derivative of the denominator is negative sine. Cleaning up that fraction, I end up with negative cosine of x over sine squared x. And then if I take the limit of the right-hand side, now I can substitute in pi over 2 from the left into that fraction negative cosine of x divided by sine squared x, and I end up with 0. Then don't forget this step. Now I need to get back to L. So I'm going to hit it with the exponent. So I'm going to take the e of the left-hand side and e of the right-hand side. Remember, the e and the natural log cancels out on the left, leaves us with L, and then e to the 0 power is simply 1. So our answer to this equation is 1.